have the pleasure to introduce Luc Steels. Luc Steels is a linguist by training. He's one of the main thinkers on artificial intelligence and robotics. He has been the disciple of Marvin Minsky, the founder of one of the founders of artificial intelligence. He's developing, exploring other alternative paradigms to the artificial intelligence. By the fact that he's a linguist, he focuses more on languages and interactions using captures, for instance, for bio-inspired robots. And I am very glad that he's with us today. So, Luc, the floor is yours.
Ah non, mais je veux dire pour... sur le... Ah, peut-être, il faut demander. Okay. Merci beaucoup, Reda. Merci pour les organisateurs pour cette conférence vraiment extraordinaire. Je vais dire quelques mots en français pour remercier les organisateurs et aussi pour exprimer que j'étais très impressionné par tout ce qui se passe ici sur le campus, l'énergie des étudiants surtout et l'intérêt qu'ils ont et en plus tout est vraiment extraordinairement bien organisé et tout. Alors je remercie tout le monde qui est responsable pour ça. Okay, I'm going to give my talk in English, and maybe we can have I have to do something, I guess. I'm going to start with a video of an experiment to show you the kinds of experiments that I have been doing with my collaborators. And it's an experiment, actually, which is addressing issues about a body model, about language, the origins of language, the origins of symbols, about evolution, about cooperation, and really about how a mind could grow in artificial agents. So I'm going to, let's look at the video right now. Okay, so I'm going to explain you more about the background of this particular experiment and why we do it and what kind of thing that it yields. But I promised also to Reda that I would first make a few remarks on what is going on in AI today. So my talk has two parts. First, a bit about the applications at the moment, and the second about these experiments. And well, it's clear that we are living at a moment of an extreme intensity in AI. And you see that in terms of the amount of money that's being invested in it. And of course, this is because people think that they're going to make a lot of money from AI. This is just one graph. You see the exponential growth. This is just expected for generative AI, which I will explain in a minute. And so, now you can say, is this boom justified? I mean, it's clearly a hype. Is it justified? And I would say partly yes. I mean, there are applications. One of them is this one, which I think are marvelous and show the incredible power of what we can do. This is for the control of nuclear fusion in a reactor, and the reactor is called the tokamak reactor, and it's about how you have to create the plasma which you have to control, and this is very difficult. And so this is an example where, of course, with a lot of other background in physics and so on, engineering, control systems, then an AI system can help. In this case, reinforcement learning and deep reinforcement learning can help to solve this problem. So this is fantastic. At the same time, also the limitations of AI are becoming quite clear. And this is an example for perception. There was a lot of enthusiasm about 10 years ago that AI systems were capable of doing image recognition, seeing a pattern and categorizing the image using convolutional neural networks, deep learning, and so on. But meanwhile, we know actually that these systems are quite fragile. You see here, is there a pointer, by the way, that I may use a pointer to point to the screen? Right, thank you. It's coming, okay. But you see there at the top are the images and their categorization correctly, and below it are for us, the same images more or less, but there's a sort of slight noise has been added, and you see that the categorization is completely different. In fact, it's wrong. And so why do we see that? It's because these systems are statistical learners. That is, they try to generalize, but we know from statistics actually that there can be a high sensitivity to the features that are used for generalization. To make a concrete example, they used to try to recognize tanks. I mean, this is an example from a long time ago. So they took pictures of tanks in the morning, they took pictures without the tanks in the afternoon, and then they showed a high rate of success. Unfortunately, it was not because there was a tank or no tank. It was because the pictures in the morning, the light is different than the pictures in the afternoon. And this is what we see all the time, sensitivity to features which have nothing to do actually with what we consider to be important. A second problem is that there's a very strong dependence on the quality of the data. And there is also a big problem because obviously data is always going to be incomplete. There's this phenomenon of the outliners, the black swans, they exist, but they are rare. And then there's a problem of inaccuracies in your data. It's just the wrong categorization, for example. Now, all of this is known from statistics. If you had a good course in statistics, you would know about these things. And another problem is that these systems are closed. They are trained once, but once the training is finished, they would have to retrain the whole thing in order to adapt to new circumstances. So, as a consequence, we see actually a sort of retreat. Musk and Tesla as promising self-driving cars. This is a statement from November 2018, and just recently, this is a few days ago, they were forced to recall all those cars because of the software in it. Now, the software in it is the AI software that was relying on the image recognition system that I just showed. And it's just very difficult in a data-driven way, statistical way, to get the kind of reliability that's needed to do this application. Now, another thing is, of course, recently the big talk about conversational interfaces. And one example is the system called Lambda, which was released in 2021, so this is quite recent, by Google. And basically, you can give a prompt, and it will write some piece of text. Amazing. If you try this, and everyone can try it, you say, wow, you could just write about any topic, and out comes some sort of description which looks like it has been written by a human. And then this has been even more recently in November last year. ChatGPT came on the scene, released by a startup company, OpenAI. They started in 2019. Now, the world got to know about it. In a few days, they had more than 1 million users. The whole thing blew up. And this company, which is a few years old, is now valued at $29 billion by the Wall Street Journal. Amazing. Now, by the way, if you want to know how it works, I don't have time to explain it, but Stephen Wolfram has actually written a very nice, very clear description, which I recommend. Okay, now, the problem is that very quickly, these systems are creating, well, let's say, something good for some people and something really bad for other people. I mean, well, for the students, you see here a student that obtained his degree writing his thesis completely with ChatGPT. And for those of you here who are tempted to try, well, if it's discovered, this was very recently in France, that the students were using it, have to do their exam again. But you see the problem, right? If the students are all doing their exercises and their assignments using ChatGPT, well, what about education? What about evaluation? Now, you would say, okay, these are students, but then there is this case of a Colombian judge who, in his ruling, wrote, I have been using ChatGPT, and this is what comes out of it. Now, wait a minute. I mean, if the law, if legal decisions are going to be made based on this system, we better be sure that it is correct, right? That it works. The other things like CNET is a news medium, and they're very respected technology news. Now, at some point, some of the people in that company started to use these conversational interfaces to write texts. And what happened is that, you see, with ChatGPT and Lambda and all the others, the thing is that although they create probable text, they don't create factual text. That means, and they call this hallucinations. Well, hallucinations is a sort of nice word to say wrong or lying, okay? But an hallucination is a fact which is simply not true. Now, the problem is that if you don't know anything and you see these texts, then you think, by God, it knows all these things, fantastic. But actually, when you know something about it, you discover that a lot, well, in some things that I tried, 80% of the facts are wrong. Now, of course, if news agencies or newspapers are beginning to produce their text like this, and these texts come on the internet, and say, you see, on the internet it says this, it must be true. Well, it is not. And so there's a destruction of the information ecosystem, the search engines and everything that we rely on. There's another thing which is also OpenAI. They produce systems like DALL-E, where you could write a text and it would create an image. Fantastic. Again, lots of enthusiasm, everybody has been trying. The problem there is that what these systems are really doing is they are taking existing images, and then they are kind of sampling, you could say, and then they're creating a new image by combining different parts to make a new collage, a combination. Okay, the problem is that, what about the copyright? Because the same approach is used for text, but it's also used for computer programs. In fact, there's a system called Copilot, where they have basically used all the programs that are published on GitHub, and I think now many programmers, maybe most, are using GitHub, which used to be a kind of non-profit organization, which everybody just put up their code, but now it's used by these kinds of data-driven AI, and then used to create new code. Now, again, the same thing about copyright, You suddenly find parts of your code it becomes part of code that's written by this AI system, but it's a collage, it's a combination of it. And so what we're beginning to see is that the companies are being sued because of the copyright issues. And one example, very recent, is Getty Images, which is suing Stability AI, which is the company that had made DALL-E and other applications like that. So you see that there's a sort of reaction. And as a consequence also, you just like with self-driving cars, you see a retreat. You say that these companies who are trying that are saying, oh, well, maybe it's not such a good idea. And one example is Meta, the Facebook, which released a system called Galactica, which is like Lambda and ChatGPT, but this one was trained with scientific papers. And they had millions of scientific papers as input, created a statistical model, and then it supposedly was producing papers, producing Wikipedia articles, supposedly all scientific. The problem is after 3 days, it had to be shut down. Why? Well, partly because the scientific community raised, an enormous protests, because these papers, they were just not true. I mean, it fantasizes fantasizes, again, I'm using a sort of positive word, right? But it's sort of made up. And the reason has also to do with the fact, as Stephen Wolfram explained also clearly in his text, that it does not choose the most probable continuation of a text. It computes the most probable based on a statistical model, but then it makes a random choice, not always taking the best one to get a kind of a sense of creativity or a sense of fluidity in the text. And so it is part of the technology itself that it does not get it right. It's not going to improve because they say, well, we just have to train with a few billion more texts. We have to make a network which is 1 billion more nodes. They're talking about trillion node neural network. But this is there's a fundamental flaw in the underlying assumptions, the scientific assumptions of this technology, which works well in certain cases, like for the control of the nuclear reactor, because it's a physical system which you can, is sufficiently stable. But if you, the physics is stable, right? The physics doesn't change so quickly, but human language, human culture changes all the time. It's dynamic. Our insights are changing all the time. And so you cannot just, statistically unpack it. So Meta, after 3 days, they got out. Google, in reaction to OpenChatGPT, released a few, when was it, last week or something, BART, their version of it. Now, immediately, the day after they released it, there was a press conference, and in the press conference, they proudly showed the system, but unfortunately, there was a fact in it which was not true. It was about the telescopes and about perception in astronomy. And so what happened to Google is the value of the company in 2 days actually diminished with $120 billion. So this is like punishment, if you want, for not getting things right. And personally, I think this is a good thing, We should realize that this is not the way we should go for many, many reasons. The same thing, Microsoft, who is partnering with OpenAI, they released a system where they connected ChatGPT with Bing, their search engine, and it's the same thing, in the beginning, they were sort of, they are getting it right, but actually, the more that people are trying it, the more that they see these things are basically non-factual. They are not, even if they're coupled to a search engine, they are still going to get it wrong. Some of the time, although if you don't know the subject, then you cannot know what is right and wrong. And this is an example. Again, Bing, by the way, is now also, I don't know what's going to happen. This is just from days ago. Huh? This is really all very recent stuff. They are at least already completely limiting what you can, the access to this system. You could say, is there a solution to this problem? As I said, a solution is not more data, is not more nodes in the network, because actually, I mean, it's still under investigation, but in some cases, it leads to worse performance rather than better performance. But I also said that there's some essential flaws in the algorithms itself. And so one way out is to combine, to kind of have a hybrid AI, where we combine a knowledge-based approach. That means that you really, are concerned with models like scientific models or models that are maybe on Wikipedia, descriptions that have been, let's say, reviewed by a large enough number of people to have some confidence in them, and to combine that with the data-driven AI. This is another example from Steven. I don't know whether he's here, but the distance, how far is it from Chicago to Tokyo? Well, ChatGPT says it's 12,000 kilometers, and it takes, 16 hours. Now, if you don't know anything, you say, yeah. But actually, I mean, it's not, it's 10,000 kilometers, which you can find if you go to a real search engine, it will tell you. And it's not 16 hours, it's 13 hours, So, okay, so I think I'm going to stop all that because I want to talk about, the second part, right, of my talk. But in conclusion, I would say that there is, as we heard also in the talk yesterday of David Chavararias, we need to be worried, because if this technology is sort of being used in the real world the way it is now, and it's spreading around, we are going to have some really serious problems. And now already in education, some schools, I mean, in Belgium, for example, say, the students have to learn how to use ChatGPT. Well, I'm not sure, It's a bit like we are going to distribute cocaine on the schools because it is a reality in our society that people, and the students have to learn how to deal with it. No. No, I think this technology should only be released if those fundamental problems are really considered. And it is like that in chemistry or in medicine. You cannot just release medicine in the world and then you say, 20% of people who take it have died. Well, this is a pity, no? We try something else. But that's what they're doing, right? Well, nobody has died yet, but okay. So now I want to come to the second part of the talk. And I want to start from this slide, which I kindly got from Reda, which is that an act is temporal or profane if it is done in a spirit of detachment from the infinite complexity of life behind it. And this is what's happening here. These AI technologies, they're just not aware of the people doing this, or they're certainly not dealing with the infinite complexity of life behind it. And so this is what I want to talk about now, is to do a really other kind of AI research, which has been going on also from the very beginning of AI, which was in the 1950s. And this is AI from this viewpoint of complexity. So let me first say a word about complexity. I think complexity science is about ways of being. the ways in which things can exist. And this is, of course, another thing that philosophers, scientists, this is what it's about. I mean, well, life is one way of being, matter is a way of being. And if we go back in the history, then typically there is this idea of a ladder, of a scale of different degrees of complexity. I put up this image here of Raymond Lull or Ramon Lullus or something, which you may know because he was one of the most famous medieval scholars who made a bridge between the Islamic world and the Christian and the Jewish world. And he had a very big influence, partly because he knew Arabic. And he wrote in Arabic, and he wrote also in Catalan, that was his native language, and in Latin, of course. And so there is this idea of the scala naturae, which you actually find, almost unchanged until the 19th century, well, let's say end of 18th and 19th century, when people started to think not about a ladder, but about a tree. And of course, Darwin was one of the firsts. But this is an image of Ernst Haeckel, the German biologist at the same time as Darwin, roughly. They start more thinking about a tree. And this is actually how then evolution in biology, evolutionary biology emerged. So now in my talk, I'm going to assume this division here. And the question that we are asking is, okay, at each of these levels, there's a different way of being. And you see, I make a distinction here between cognition, mind, and consciousness. I'm not going to say much about soul, partly because this is a really difficult topic. Also less about consciousness, which is also a very difficult topic, and which I think, from an AI point of view, we can think about it, but very few people are doing it, but it's beginning at the moment. And then you have these other levels. And so the first question that we ask, taking this point of view, is what is the way of being? What is the stance from which you need to take that can predict an entity's future behavior or explain why it behaves or has behaved in a particular way? And so if I make a little table like that, well, sorry, I don't have a pointer, but the physical level is quite obvious, right? You take a physical stance. So you can explain the system in terms of physical laws, physical observables, and so on. Now then you have the living level of the living organisms, and in order to understand them, you need to take a functional stance, in terms of functions, subfunctions, but also faults, repairs of faults. And the important difference there is what Francesco Varela and Maturana called autopoiesis. That means these systems are not just there, like a rock is there, and well, it is. But a being needs to construct itself. It needs to self-construct, self-repair, and so it actually has to create itself. So this is all the living entities, and then we get to cognitive agents. And so those are entities that also have to reconstruct themselves, but at another level, at the level of cognition, you could say. And so these, to do that, you need a nervous system or some computational information system. And you need, in order to understand them, to predict what they're going to do, you have to think in terms of goals and what they want to achieve. Now then we have the mental level, and these are, well, like humans who have a mind, right? And at least for me, well, sorry, in order to describe and understand these systems, you have to take an intentional stance. That means you have to think in terms of beliefs, desires, intentions. And this is, this term comes from Daniel Dennett, the philosopher. And so when somebody is doing something, when somebody is throwing a pot, not throwing, it's just a pot is falling from a balcony and is hitting a pedestrian, on the head. Now, in order to describe that, you can use a physical stance. But if you want to understand and you see a person pushing the pot, then it's in terms of why is this person doing it? Well, maybe there was an argument, with the other person, or he tried to kill him or something like that, right? So you have to take an intentional stance in order to describe and predict what is happening there. Now then there's another level, which is that of conscious entities. And here we get into more difficult waters, but in any case, in order to understand, you have to take a viewpoint that such entities, like we, there's a form of awareness, okay? There's a self recognition, a self, model also that allows these agents to think about themselves and also to have subjective experience about themselves. So these are the, I have to do this quickly because of time. But then the second question we ask is, what are the fundamental innovations that made a new level of being possible? And then here, this is where we get in the domain of complex systems, because we heard a talk, for example, yesterday by Steen Rasmussen, which was about how you go from the material to the living. And I'm sure Stuart Kaufman will talk about this also. And so we know, that actually part of it is an information system, the genetic system, which is instructions, genes, that the organism, the cell, for example, can use to construct itself, to maintain itself. And so you see that there's a new form of information representation happening, and then a way to use that in autopoiesis. Now, cognitive systems is also an innovation in the sense of information representation, but it's information about the world. And it is also information about what actions to do in the world, when, and how to do those actions. And the big thing, of course, is just like a cell can build itself based on its genetic system, the cognitive system also builds itself by learning. The neural system builds itself. Now then, at least I believe that when we go to mind and to the mental, then symbols play a very important role. And the symbol is just something, a physical thing, which is standing for something else. And so something else can be some object in reality, but it can also be a way of categorizing reality and a way of conceptualizing the world. And so there we get into another level of being, how minds that do this kind of symbolic representations and reasoning and constructing possible worlds actually, rather than having to deal with the here and now all the time, they can deal with imagined worlds and possible worlds. And then at the level above, we get yet another representation actually, which is representation of the self and how all that works. So reflection, the meta level, which I'm sure Chetan will talk about, are the kinds of things that are crucial at this to that level. And the third question that in complex system science we like to ask is, how do beings of a certain type, how do they increase their own complexity and the interaction with others? How structures are forming among the entities of a certain kind. In other words, we ask the question about evolution. And there, we have by now really a wealth of ideas on how this could happen. Well, one idea is, of course, self-organization. And self-organization, you have it in chemical systems, you know, the Belousov-Zapitinsky chemical reaction, which is forming structures either in space or in time. You have in the weather, you have all sorts of self-organizing things. So this is one example. Another example is emergent behavior, how new behaviors can emerge from the interaction of certain forces that have a side effect, which can have new functionalities for the system as a whole. You know, there's level formation, there's selection, of course. Now, I don't have time to start going through a complete list, but for sure, this is what I think the big contribution of complex systems is, to give us an arsenal of ways of thinking about this kind of increase in complexity, the origins of order, and so the idea is also that there are some mechanisms that are operating at each level, but of course on the representations and objects on that level. Another example of work that you know, was very useful to me was to work with evolutionary biologists, and one of them is Urs Zatmai, to, you know, because in biology, of course, you have all these mechanisms at work, but the same mechanisms, this is my main point, are also important at the cognitive level and at the level of mind and at the level of consciousness. Okay, now, so this is complex systems science and its application to the different levels. And in physics and chemistry and in biology, I would say they are much more far advanced in this kind of complex systems thinking than we are in terms of cognition and mind and consciousness. Now, the second big idea is that how are we going to research these things? And you can make mathematical models, you can do computer simulations, but then there's this idea of the artificial. And the artificial, like in artificial intelligence, but also in artificial life, is a methodology. It's basically saying that in order to investigate how complexity emerges and so on, we are going to build artificial systems that we design and build. Building is very important. And then see whether this complex phenomena can emerge in those systems. And so this is the idea behind artificial life. I put up Chris Langton here, who has done a lot to show this idea for, let's say, the living world. I did a lot also with Rodney Brooks, who's an MIT professor in robotics. And together with him, you know, we talked about the artificial life route to artificial intelligence. This is all in the 90s, by the way, which is really trying to use these ideas of complex systems to move up from a living system or from a robotic system, which is sort of, you know, has functions and sub-functions and all that, in order to understand how cognition may emerge and then how mind may emerge. Well, I already mentioned Steen, who's also doing artificial life experiments, and not just talking about how life may originate, but as he showed in his talk yesterday, also actually trying to do it for real, with real chemistry. And so I'm running out of time, of course, as usual, but I will try to be disciplined because I think I started a little bit later. So I'm just going to give you a hint of the kind of experiments that we do. And I've been doing this since the 90s, so by now we have like 20 or so, 30 experiments. I should say that, you know, one measure of complexity for experiments is the number and the time of the graduate students that you need to do an experiment. And it's high, I can tell you. So sometimes these experiments took 10 years to do. And there's, several PhD theses are required to do one of these experiments. So it's really difficult. Even if they look simple, they are complicated. Anyway, the first example, I just give two examples. The first example is an experiment that I did together with David McFarland, who is an ethologist. He's from Oxford, student of Tinbergen. And so I learned a lot from him about animal behavior and animal cognition. And so we set up an experiment which started from this experiment by Walter Gray, who's a cybernetician, a British cybernetician, who built in 1950 these robots, which he called Elmer and Elsie. They were actually cartoon characters at the time. And they are autonomous. They have a battery, they have electronics, they have sensors, they have actuators. And this is very important. The research we do starts from embodied entities, right? They are in the world, they're behaving in real time, they have sensing and actuating, and this is the starting point. But then Walter Gray also constructed this charging station. And so his robots could glide into the charging station to recharge themselves. So we actually started from rebuild the experiment, and this is the setup. This happened in Brussels in the AI lab that I started in the 80s. And so you see in the back there, you see this yellow light with the charging station, and the robots can slide into it and recharge themselves. And then you see that we used Lego robots. You see, here you see them. Well, when you came to my lab at that time, you would think it was like a kindergarten, a playroom full of Lego blocks and people playing with them. And partly, of course, we didn't have a lot of money, but also because you can build different bodies, experiment with them, and in a relatively cheap way. But these robots, they had a processing board on it, and so they had sensors and actuators and the whole business. So Lego robots. And then you see this other object there, and this is the second ingredient we brought into this experiment, is competition for the energy in the charging station. And so if you think about the biological world, there's always, if there are more than one entity, there's competition for resources, and also the living entities have to work for their, they have to gather food, they have to hunt for it, share it with others. And so we brought that element into this ecosystem, and we also brought in more than one robot, okay? And now, once you have these ingredients, then you can start doing experiments. And I cannot really go into much detail, but I just give quickly two examples. One of them is we try to use as much as possible emergent behaviors. That means we didn't want to program things. We wanted, of course, you have to program some simple behaviors, but then we wanted to see how out of these simple behaviors, we could have emergent behaviors that were more robust and that were, discovered, you could say, by the robots themselves. And so it turns out, like for going to the charging station, you have some simple behaviors. One of them is forward movement, which is basically a combination of increasing or decreasing your motors in order to reach a certain level of movement. There's phototaxis, which is attraction to light, based on two light sensors, and they would influence the motors, in order to, they wouldn't measure actually, or this behavior would not measure, but it would sort of dynamically try to steer in the direction of light. and then touch-based obstacle avoidance, which is based on touch sensors. It turns out when you just throw in, the these behaviors, then actually we got the robots to go into the charging station, though we did not implement this kind of go to the charging station behavior. But then there's another thing is, in evolution, you also often have the fact that emergent behaviors become stabilized through genetic evolution. And so here, we're dealing with a cognitive system where the stabilization of a combination of behaviors with a purpose, with some functionality, is actually achieved by adding some learning to it. In this experiment, we added Hebbian learning, so that the robot would learn actually to avoid, not to bump into obstacles and retract from them, but to use, after a certain time, infrared sensing, so that it didn't need to bump. It could do obstacle avoidance based on infrared. I'm doing a bit of hand waving here. There are papers that describe all these experiments in detail. Now, I'll skip this one. So now I want to give a second example, which are experiments that we have done to go from a cognitive system to a system that had mental capabilities, in other words, that would be able to deal with symbols. And as before, we didn't want to implement symbols, or we didn't want to design, our symbols into these robots, but experiments that symbols would emerge actually in those experiments. And the first one is the talking heads experiment, where you had two talking heads, to cameras that can look into the world, and two agents, each using the different cameras to look into the world, to come up with a picture, to categorize, what was going on, and to use language to tell the other one to which object in the world he should pay attention to. Again, I can't go into much detail, but we did these experiments with lots of agents, with cameras distributed in different locations, I think there's something in the transition from one computer to another, so you have to turn like this. But this is one example of this experiment that is showing, the right axis is time, actually, and the left, at the bottom here, is which word became dominant in the population for expressing a certain category, like left or red, or and so on. So you see that there's a sort of winner-take-all dynamics which is taking place in this group of agents without any central control, without any predetermined language or anything like that. We did a lot more experiments. I cannot really get into it, but this one about color is particularly making the point of a structural coupling between the emergence of a vocabulary and the emergence in each agent of a conceptual repertoire, ways of categorization, and through language, actually, they kind of co-evolve, if you want, or share the same system. So I can't do much more here, and also experiments about space and so on. And so we are back to the video that I showed in the very beginning, which is an experiment about body and actions in the world. So, conclusion, I think that this approach, which is a complex systems approach, asking these questions at each level, how does complexity arise, how does that level sustain itself, is helping us to understand cognition. Now you say, well, what are the applications? Well, let's here think not directly about applications, but about advancing the fundamental science of understanding how cognition and mind and maybe consciousness are possible. The synthetic experiments, the artificial intelligence or artificial life experiments, they are difficult to do, they take time, but it's, in my view, the only way in which we can really understand the problems involved and also validate potential ideas we have. Because I'm just giving one example after another here, but these examples, I can assure you that the first time nothing worked. And of course, sometimes robots would explode because they overcharged and so on and so on. So it is difficult to do, but I think it's like, research into flights. I mean, you have to, build flying machines in order to really discover. And that's the way we do it, like the Wright brothers. And so this is, the last point here is really for students who are here. There's a tremendous number of open problems which are ready to be attacked. And the trick is to find the problem, to decide about the problem, and then it can be, like thinking about color, for example, color categories, color language. What does it mean to use color in interaction? Can we set up an experiment for the origins of color categories in such a kind of setup? These are all examples of studies that can be done that would advance, just like they do in biology actually, studies for showing how certain forms of complexity can arise. I'm very sorry, this is the final slide here, and I'm, while maybe, I just ending with this, about experiments going towards the idea of self-conscious robots and looking at themselves, trying to figure out their body, what it is. And anyway, I thank you.